All right, welcome back to Dynamic Topology. This is the series where we're not just reading about math, we're actually building it together right from the ground up, following Gordon Whyburn's amazing blueprint. Let's jump right in. So let's start off with a really interesting puzzle. We're all pretty comfortable with the idea of a sequence of points, getting closer and closer to some target. But what if we zoom out? What does it even mean for an entire set, a whole blob of points, to kind of bunch up and converge to a single spot? How would that work? Well, to even start answering that question, it turns out our good old friend the sequence just isn't quite up to the job. We're going to need something more powerful. We need a whole new tool. I mean, think about it. Sequences are fantastic for tracking individual things in a nice, orderly line. But they really struggle to capture the behavior of a whole collection of points, like a shape or a region, as it shrinks and closes in on a target. It's like trying to describe a flock of birds by only watching one of them. Our old tool has its limits. It's definitely time for an upgrade. And that brings us to our new tool, straight from Whyburn's text. It's called a directed family.
Okay, I know. At first glance, that definition looks pretty dense, a lot of formal language, but hang with me, because the idea at its core is actually really simple and elegant. All this rule is doing is giving our collection of sets a built-in guidance system. It makes sure they're always shrinking and heading in a consistent direction, so they can't just scatter randomly. Let me show you what I mean.
We can turn that formal definition into a really simple three-step test. Here's how it works. Step 1, you just grab any two sets you want from your collection. Step 2, find the area where they overlap, their intersection. And now for the really important part. Step 3, you have to be able to find another set in your collection that's even smaller, one that fits completely inside that overlap. If you can always do that, no matter which two sets you start with, boom, you got yourself a directed family. It's this guarantee of always getting smaller and more focused that makes them so powerful. Now, building on that, we have this idea of an underfamily. You can think of it as a more refined subcollection. It's like a subsequence, but for our families of sets. It's nested inside the original family, and it follows the same narrowing path, but maybe it does so a little more efficiently. And believe me, this concept is going to come in handy very, very soon. So, we've built our new tool. Awesome! Now let's put it to work. We're going to use it to define two really important but very different ways a family of sets can approach a point: convergence and clustering. First up, convergence. Now, this is a pretty strict condition. It means that if you take a point P and draw any open bubble around it, what we call a neighborhood, no matter how ridiculously tiny you make that bubble, eventually the sets in your family have to get so small that one of them gets completely trapped inside it. It gets totally captured. And then we have the idea of a cluster point. This one's a little more relaxed. A point P is a cluster point if every bubble you draw around it intersects every single set in the family. Notice the difference? The sets don't have to get trapped inside the bubble. They just have to constantly graze it, to always be hanging around nearby. And this really nails the difference, right? Convergence is all about being contained. Sooner or later, a set gets completely swallowed by the neighborhood. Clustering, on the other hand, is just about intersecting. The sets just have to keep touching the neighborhood, staying close. It's a subtle distinction, but it's absolutely critical. All right, for our last section, let's take these brand new ideas and see what happens when we use them to test the properties of a really special kind of mathematical space. We're going to talk about the Hausdorff property. Here it is. This is our challenge. We're going to prove this fundamental theorem. And what it's really telling us is something beautiful. In these special, well-behaved spaces, convergence is unique. If a family of sets is heading towards one specific point, it can't also be clustering around some other point on the side. It has to commit. So what makes a space a Hausdorff space? The property is actually wonderfully simple. It just means that for any two different points you pick, you can always draw a bubble around each one in such a way that the two bubbles don't overlap at all. You can always cleanly separate them. That's the whole idea. So, how are we going to prove our big theorem? We're going to use a classic technique, proof by contradiction. Basically, we'll assume the opposite of what we want to prove is true, and then show that this assumption leads to a complete logical mess. So, step 1, let's assume the impossible. Let's pretend we have a family that converges to a point P and, at the same time, has a completely different point Q as a cluster point. Okay, step 2. Now remember what kind of space we're in. A a Hausdorff space, so we get to use its special power. We can draw a nice little bubble, we'll call it up, around our convergence point P, and a totally separate, non-overlapping bubble, UQ, around our cluster point Q. This separation is the key to everything. These two bubbles are completely isolated from one another. Now let's think about the consequences. First, we assumed our family converges to P. Well, by the very definition of convergence, that means our sets must eventually get so small that one of them falls completely inside that first bubble, U. So, we know for a fact there's at least one set in our family, let's call it F gamma, that is living entirely within the walls of U. But wait a minute. Remember the other half of our assumption? We said Q is a cluster point. And the definition of a cluster point says that every single set in the family has to intersect the bubble UQ. Not just some of them, all of them. And that has to include our little set F gamma that's supposed to be trapped inside UP.
And there it is. The contradiction. The whole thing falls apart right here. We've created an impossible situation. How can the set F gamma be entirely inside the bubble U, while at the exact same time it has to touch the bubble UQ? It can't. Those two bubbles are completely separate. It's like saying you're entirely inside your kitchen, but you're also touching the mailbox down the street. It's logically impossible.
And since our initial assumption led us to this nonsense, that assumption must have been false to begin with. And just like that, our powerful new tool, the directed family, let us prove this fundamental property about Hausdorff spaces with absolute clarity. It worked! So we just created a new way to think about convergence for sets, and immediately used it to discover a deep truth about the very nature of these spaces, which, of course, leaves us with an exciting question to think about for next time. Now that we have this powerful new tool in our hands, what other doors in the world of topology is it going to open for us?